I'd like to introduce our next speaker, Filippo Valsorda. Is that right? Okay, close enough. Anyway, it's not an easy job doing this, let me tell you. Better than average, there you go. Okay, that's pretty good. So his fun fact is that he was once in a group hug at DEF CON, is that right? With Kevin Mitnick?
Yeah.
There you go. Take it away, Filippo.
Okay, this fun fact actually usually works at security conferences. I get it, I'm not a security conference. Okay, also, yeah, nothing. Okay, I'm Filippo Valsorda. I'm here to tell you essentially how to get free test coverage without doing nothing. Who's interested in that? Good, okay, you should be writing tests, not listening to this talk. Okay, whatever. First, something about me. I work at Cloudflare. I do cryptography engineering and systems engineering. I'm one of the main developers of the DNS server at Cloudflare. Cloudflare is a CDN. We don't host. We cache and sit in front websites, and when you connect to a website, you connect to us. So we have this global DNS infrastructure, and our DNS server is completely in Go. Pure Go, by the way, which means there's no even C Go, and since recently, and that really makes me forget. Okay. There are voices. I mentioned Seago and voices start. Okay, no, I mean, I'm scared as you are, okay. So, anyway, past making bad jokes and writing DNS and DNSSEC implementations, I often mess with cryptography, security protocols, security vulnerabilities. You might actually have used my Herbleed test in April 2014, well, it's been a while. Or fell for my WhoAmI SSH server that told you who you are on GitHub when you connect. If not, it's still up if you want to play. Anyway, you might have not ever seen neither, but the point is that there are two Go tools, and they wouldn't have been possible if I didn't have Go with the excellent standard library and performance to build them. But you will hear a lot more about the standard library and the crypto library from my colleague later in the day. So, let's get to it. Here is a function. So, you will often hear from people that you shouldn't put code without error handling on slides at conferences. So I did something more, and I put a bug on the slides directly. So this function has a bug. What this function's supposed to do is parse something from the network, think a DNS packet, wonder where that's coming from, and just parse this binary encoding where you write a byte with the length of the string that will follow, and then you read that many bytes of string, and then again 1 byte with the length, and that many bytes. So like you write a byte 13, and you read a string of length 13 from this buffer byte you got from the network, from some evil user somewhere, okay? And you have this in production, and it's reading stuff from the network. And this is gonna crash. But you obviously want to be cautious, so you write tests, right? It's in production, it's exposed. So you write tests, and you write your, two unit tests for 1 string, for 2 strings, and then you start thinking about corner cases because you want to cover those too. And so you write a test for the empty string. Maybe that will crash. It doesn't. All tests pass. Sounds good. You ship to production, right? The DNS server crashes, and everything comes down flaming. Can you see how I actually tried this talk a couple of times? People don't actually get it the first time, so I'm terrible at making examples, apparently. But the thing is that you can see how string length here comes from the input, and then it's used to slice something. Slice out of bounds says anything? Some heads nodding, I can probably go on. Okay, so I'm not here to tell you about bugs, I'm here to tell you about techniques to find bugs. Fuzzing. Who heard of fuzzing already? I'm useless. Yeah, okay. Fuzzing, anyway, is the technique of testing programs that take complex input, or anyway inputs that come in the form of string of bytes, or at least that's the fuzzing I'm going to tell you about, and keep changing these inputs automatically with a computer until the unexpected behavior happens. Unexpected behavior can be anything. Can be, you know, authentication systems let you through even if you don't have a password, or more in our case, crash, panic, OS exit 1, something goes wrong. And how it works, what's special about fuzzing is that it's not a user or your QA department that tests your software, but there's a program that just goes and keeps generating new inputs until it finds something. So how it generates these inputs? It takes some examples, some starting point that you give it, which is, for example, something we pulled from our unit tests, and it starts mutating it. And here is where a lot of smart people actually put real thought into to figure out all the different ways that can trigger, you know, things to happen. So sometimes you flip some bits and change one byte to see if something changes, and sometimes you duplicate the first half, or maybe you duplicate the second half, or there are a whole list of different things you can do. You add a random byte at the end, you replace the first byte with a random byte, you cut the output in half, you keep trying things. But the problem with that is that, well, it will take forever for that to find a real bug in a real code base. It happens. But still, this is pretty dumb, right? It just goes and throws stuff until something happens. It doesn't really know what it's doing, okay? So if you need I don't know, you have a PNG image, okay? And you want to trigger something that happens when you use a specific extension. I don't even know if PNG has extensions, but bear with me. You will have to find the exact bytes in the header and then maybe the exact value. You're never going to be so lucky to set them both at the same time by chance. Enter coverage-guided fuzzing. Coverage-guided fuzzing uses code coverage to figure out what it's doing. So code coverage, if you wrote tests, you probably already know what that is. There's a really good blog post on the Go blog that will tell you how it works in Go. And essentially, the source is instrumented, and the program that is managing it will know what lines of code got hit. So coverage-guided fuzzing uses that to figure out what happened when a mutation was introduced. So if there's, I don't know, invalid value somewhere, and it keeps setting that, it will notice that every time it does that, the coverage of the file gets to, 10 lines, and always the 10 lines, and it will drop that and not, keep pursuing that mutation. So, for example, let's take this. Sometimes people complain that my slides, the text is too small, so I decided to push it to the extreme. No, you're not actually supposed to read this, don't worry. Just look at it from afar, which is actually what the coverage-guided fuzzer will do. The coverage-guided fuzzing does not, read the source and doesn't do static analysis. It will just look at what lines are hit, okay? So, let's say that you have a bug there, not a real bug. Okay, there isn't actually message 10 millions indexed there. But, and let's say that your example input, the first thing you start fuzzing with, the test you pass to your function, triggers these lines, okay? You start the fuzzer with example test, it passes the binary string to your function, and these lines light up, okay? But the bug is deep there, right? It will not manage to hit the right case here, and then the right case here, just by randomly doing stuff. Agreed? Okay, so what does it do? it will keep changing stuff until it sees the coverage change. It will not keep changing stuff and, you know, just change the indexes here that will not actually run other code. Every time it does a mutation that doesn't change the coverage, it will discard it, mostly. So at some point, it will hit some mutation that will finally pass this case here and light up this new code path. It will notice, and it will go like, okay, this new input causes your function to do something new. This is a new path. It will take this and put it on a queue. And next it will start mutating that input. Okay? It discovered how to get to this, and now it wants to expand from there. So it will keep doing and doing until eventually it will finally put a dot in there, put a dot, light up that line of code, panic, report it to you, you will find the bug, fix the bug, go home. Done. Get the point? Okay. So this actually, this might seem like, you know, crazy talk, and this might work for that message 10,000 bug, but doesn't actually work. No. American Fuzzy Lob. American Fuzzy Lob is an extremely efficient, effective, and popular fuzzer by Michael Zaleski. I can't pronounce that. he has more problems than me, probably, with pronunciation of his name. It uses compile time instrumentation in the, I think there's LLVM and the GCC modules to insert essentially, yeah, instrumentation that will tell the fuzzer what the internal state of the program is, including code coverage and some other bits of the state, and use that state map during fuzzing to figure out if new inputs do new interesting stuff. It found, I think, dozens of bugs, security bugs in C and C++ programs. And I'm not talking about, you know, random programs. I'm talking about, anyone heard of the bind denial service at some point? That was AFL. Someone used it to refine Herbleed by just pointing it at the right part of the OpenSSL source. It wasn't found like that, but you could have found it like that, without knowing what we were looking for. Okay, I'm not actually here to tell you about AFL. It's awesome. Go read directly from the author's voice. There's white paper. You'll get the slide. Well, okay, so you're telling me it finds security bugs. This is a security talk and I'm just confused and entered the wrong theater? No. Obviously no. Obviously, coverage-guided fuzzing is great at finding security bugs because it's great at finding corner cases, okay? What it struggles for is lighting up the most lines of code possible, okay? The ones you didn't write tests for. So, in C, this means obviously finding places where memory is mishandled, and that usually is leads to security vulnerabilities. And security researchers love finding those, so they will take any software, run AFL on it, and find vulnerabilities, publish them, become famous, rich, and leave. Doesn't actually work like that, but you know, we like to hope. In Go, we are still happy to find bugs, right? We are not security researchers, because probably there won't be much more than a denial of service, but still we'll be happy to light up those corner cases that crash our programs. We love finding bugs, not having bugs, but finding bugs. So, enter Gofuzz. Gofuzz essentially takes the technique of AFL fuzz, inspired by AFL fuzz, and applies it to Go programs. It uses AST rewriting, just like the coverage, the test coverage tools, to instrument the source of your program, and then uses that to guide fuzzing. It found hundreds of bugs in the standard library. I'm not going to tell you exactly how it does AST manipulation for two reasons. One is that Dmitry Vyukov, the author of GoFuzz, actually gave an excellent talk at GopherCon on the inner workings, with some of the inner warnings. And you will hear more about AST and source code instrumentation later in the day. So, it found real bugs in the standard library and the compiler. You say, you know, how many? Many. Okay, so back to our bug. You remember our bug? Okay, so you can probably see where this is going maybe, but still, remember that the problem is that when the first input byte, the one that tests the length, is longer than what's actually there, it will panic. So let's see how to use fuzzing to find this bug. So how Gofuzz works is that you write a fuzz function. Okay, you write this function that takes a string slice of bytes, and that slice of bytes is what the fuzzer will mutate, and the fuzzer will take care of that. You don't care, and then pass it to something that you want to test. In this case, our parse strings function, okay? And that's essentially it. That can be enough. You write that in your package. It's a top-level exported function of your package. You can put that behind a build tag if you don't want to compile it every time. That's okay. And Gofuzz will keep running that function in a loop with mutated inputs until it crashes or exits one. This is very fast, because obviously it's inside your same program. And also you can write wherever you want in the fuzz function, but we'll get to that. So how you run it, how you use it, is that you use Gofuzz as a compiler. Okay? It's a wrapper at the end of the day, but you use Gofuzz to build a zip file that contains everything. Then you prepare a corpus, which is example inputs. Because yes, the fuzzer might keep trying until it finds something that lights up, you know, the path of a PNG library. And AFL actually managed to do that, and that's scary in a, you know, machines taking over the world kind of scary. But you probably don't want your fuzzer to have to do that, so you want to give it some examples, starting points. So you make a work there, a corpus folder inside that, you put our usual example there, okay, and you run Gofuzz. There. And it will start finding new new inputs that may light up different areas, and it will eventually crash it. So here is what the folder will look like, many different, you know, your example and other corpus that it found, and the crasher with some helping files. This is the output of the crash that it will keep for you with, lo and behold, runtime error, slice read out of bounds. And the crashing example, which is a single byte ASCII 0. Because Gofuzz will actually try to make it as small as possible, so that it's easier for you to then triage the bug. And it will also give you a quoted version that you can stick in a unit test and have regression tests covered too. So you probably figured it out by now, but what Gofuzz did was put 0x30 here, and then string length ended up past the end of the input. It found our bug. So this is all again fuzz talking. That was a bad pun. Anyway, real-world examples. I work on DNS servers. At Comfort we use this awesome library, GitHub.com MIG DNS, and it's very good. We use it to parse the packets from the network, but you know, we use it at Comfort to parse the packets from the network. Don't panic is a very good mantra. So obviously we saw an occasion to fuzz it. So here's what a fuzz function might look like. Okay, it's very simple. It takes the usual raw message from the fuzzer, it unpacks it, it also tries to repack it, because hey, maybe it will hit a crash trying to repack a strange type that the fuzzer managed to build. And then it will just, return 0 if the thing failed, to tell the fuzzer, well, yeah, but this isn't a real packet, it didn't really work, and return 1 to give it a bump in priority. That's all. So here's a bug that it found, and it found tens of others. There's a blog post about this fuzz run. Anyway, this bug is exactly in the huge function I showed you before, not the message 10,000 one. And it was a pretty hard one to find because it had to, run other code in other functions first to get the offsets in the wrong positions, and then call this one that would discard the offset. And anyway, no one noticed that, but the fuzzer managed to run all this different code at the same time, and as soon as it hit it, crash, panic, burning, flames, etc. So, my last point. The best people to write unit tests. Who should write unit tests? Whoever is writing the source. Agreed? I shouldn't come and write the unit test for you. You shouldn't come and write the unit test for me. Right? You're writing your source. You know what needs testing. You know what you want to check. So that's the same thing for fuzz tests. You're writing your source. You should be writing your fuzz functions. Because if you think about it, fuzzing in the security world is about finding security bugs once off that the developer didn't find. But what I'm here to tell you is that fuzzing is an effective way to test programs that take complex inputs. Okay? So, you know what needs fuzzing. In a DNS library that I use every day, I knew that the thing that needed fuzzing was dns.message.unpack, but it's not obvious. So if you commit them, other people will then come and maintain them and expand the fuzz functions. Just like you commit unit tests, you don't keep them on your laptop, because I know you can run them on your laptop, and it works on my laptop. But if you commit them, then you have contributions and people can learn from them, and then you can run them in continuous integration. There's no reason you shouldn't run fuzz testing in continuous integration. Also, you can keep the corpus, all those different inputs it generated over hours and hours, and you can keep replaying it. And the fuzzer will be much faster because it will have examples of everything that lights up everything, and it will take no time to find the new paths you just added and fuzz those. And you can use this big corpus across refactors, across different annotations. There's a lot to be said. So, yeah, this is essentially another slide to make the point again, but I will spare you. One final bonus. It's not just for crashes. You write the fuzz function, okay? So if there's anything you can think of that you can test with an if, and that should never happen, you can fuzz that. So, real world example. Our DNS server keeps a sync pool of byte slices. Makes sense, right? Why should it allocate a new byte slice every time it sends out a packet? So, it would, in production and not in staging and not in development, it would have this bug where some bits in a bitmap in one of the DNS records would get set magically. Took forever, but essentially, I figured out that it would keep doing that because it would rewrite over dirty buffers that had already bits set, and it would not override them. So what I did is write a fuzz function that would first packet a message, unpack the message, pack it to an empty byte slice, then pack it to a completely full of ones byte slice, and compare it. Are the two different? It means that some bits leaked from the buffer underneath. That shouldn't happen. It will tell you when it happens. And that's it. Thank you.
Okay, well thank you very much, Filippo. That was great. We don't have any more time for questions, unfortunately. But that was excellent. I'm sure you'll be hanging around the rest of the day if people want to talk.
Absolutely, and I take questions on Twitter or anything.
There you go.
Thank you.
Thank you very much.